In 10.1, we're going to introduce some more trig identities. Let's briefly go over some of the major ones that we've looked at so far. The reciprocal identities, so cotangent is 1 over tangent. And remember, tangent is also 1 over cotangent. They're reciprocals of each other. Secant is equal to 1 over cosine. Cosine is 1 over secant. Cosecant is 1 over sine. Sine is 1 over cosecant. Then we have the quotients, and that just means we can write tangent and cotangent as a quotient or a fraction. Tangent would be sine over cosine. Cotangent would be cosine over sine. Pythagorean identities, sine squared plus cosine squared is equal to 1. So remember, that comes from the unit circle, whose equation is x squared plus y squared equal to 1. Sine is our y, cosine is our x, so replacing the x and the y with sines and cosines, we get sine squared plus cosine squared is equal to 1. And then from that original Pythagorean identity, we can get 1 plus tangent squared is equal to secant squared, and 1 plus cotangent squared is equal to cosecant squared. We also had our even and our odd functions. Cosine and secant are only even functions. And what that means is that if there is a negative in the argument, we can just get rid of it. But the other four, all these four, the sine, cosecant, tangent, cotangent, these are odd. If it's an odd function, that just means that if there is a negative inside the argument, you can bring it out in front. So what we're going to do next is we're just going to kind of play around with all these identities and just get comfortable with them. It's kind of, sometimes it's difficult to see the algebra properties that we have had before when we apply them to our trig functions, because the trig functions just have so many letters. So in the first example, we want to write this expression as a single trigonometric function, or a power of a trigonometric function. And that just means write it as one trig function. And here in this first expression in example 1, I have 3 trig functions. Right away, I can see that cosine over sine, it's that quotient identity, that's cotangent. So I can replace the cosine over sine with cotangent. So this will just be cotangent of theta times cotangent of theta. So I've gone from 3 trig functions to just one trig function, which is just cotangent, but then I can write this as cotangent squared of theta. So it's a power of a single trig function. Well, let's continue on kind of manipulating and playing around with these identities. In example 2, it says write sine of theta in terms of cotangent. If I look at my identities, it would be nice if I had something where it said sine of theta is equal to, and then it was equal to something with just cotangents, but I don't have that. So when it says write in terms of, that means we need to write sine of theta equal to something with only cotangent. So what I'm going to do first is I'm going to do, and people can do these in different ways, I'm going to choose to first write sine as 1 over cosecant. Because I know by that Pythagorean identity that I have 1 plus cotangent squared is equal to cosecant squared. Or in other words, cosecant squared of theta is equal to 1 plus cotangent squared theta. And the only reason why I'm doing that is because I now want to replace that cosecant in the denominator with something with cotangent. So I'm going to solve for the cosecant by squaring both sides and remembering that there's a plus minus in front of this square root. It becomes a plus minus the square root of 1 plus cotangent squared theta. You know, if I knew what quadrant this was in, I could choose the negative or the positive, but I actually don't. So the best I can do is replace the denominator with both the plus and the minus, square root of 1 plus cotangent squared theta. So here all I've done is I've rewritten sine so that it's in terms of cotangent. And manipulating these trig functions becomes really important. Now in the book, it might have you rationalize the denominator. But I don't expect you to do it for expressions that are kind of complicated like this. But if you did have to rationalize the denominator, you would simply, oh, now I'm going to run out of space. Get rid of the square root in the denominator by multiplying top and bottom by the square root. You don't have to worry about the plus minus, that can stay where it is. Maybe I should have left a little bit more space. So this would be easier to see. So that would be, I'm going to bring the plus minus out in front, square root of 1 plus cotangent squared theta. In the denominator, the square root cancels. So you could write it like this as well, with the denominator rationalized. Looking at more examples of manipulating these trig functions, in example 3 it says write cotangent of x plus cosecant of x in terms of sine and cosine. So that's a common technique we have. Sometimes when our trig expressions look very complicated, we will change everything to sines and cosines because that's more familiar to us. So let me go ahead and I'm going to just rewrite this expression, the cotangent of x plus the cosecant of x. So cotangent is cosine over sine, and cosecant is 1 over sine. So I have written it in terms of sines and cosines, but that's not simplified because I still need to add those two fractions. So remember, when you add fractions, you need the common denominator, but I have a common denominator, and that's sine. So I just add my numerator over my denominator. And this would be written in terms of sine, cosine, and also simplified as well. Notice that instead of theta, I have an x. The variable in the argument can be whatever we want it to be. It could be hearts, happy face, doesn't matter. And in example 4, I have the Greek symbol beta. It looks like that weird B, just so that you can get used to using different symbols. So if we had to write this expression in terms of sine and cosine, if I were to replace the secant with 1 over cosine and cosecant with 1 over sine, I would end up with a complex fraction, which is fine. But I would rather do this first because I know that I'll end up with complex fractions. So I think I would rather separate the secant and the cosecant. For me, this is easier because now watch what happens when I change the secant to 1 over cosine. And changing the cosecant just means I'm going to flip this to sine of beta. And if you wanted to write it over 1, you could. So now you can see all I have to do is multiply in the numerator and the denominator. And I've written it in terms of sine and cosine, but it's still not simplified. I could write this with less symbols by changing sine over cosine into tangent of beta. So that's a simpler form. Now I am going to show you what it would look like if you didn't separate it, which is completely fine. If you kept it the way it was, then secant would be 1 over cosine of beta, and then you have your fraction bar, 1 over sine of beta. So you see how we have this complex fraction, which we would then have to change to the top divided by, looks like a plus, the bottom. And then we would change this division to multiplication, which it's fine, it's doable. And we're back to where we were on the other side, combining this into sine cosine. And there's always more than one way to do these. So if you're looking in your textbook, your solution may not follow the form that they went, but as long as you get to the same place that they got to in the book, then you're fine. If you're not sure if you simplified something all the way and you check your answer, and your answer doesn't match what's in the textbook, just see if you can get from your answer to their answer, because yours just might not be simplified all the way. So now in example 5, it says write in terms of sine and cosine and then simplify. So the problem with this one is when I write this in terms of, in this case it would be, it's cotangent, right? It would be 1 plus cotangent squared is going to be cosine squared over sine squared. So you see what the problem is? I end up with this complex fraction and I don't want to play around with that. So instead of writing it in terms of sine and cosine, I'm going to cheat and I am going to use that Pythagorean identity, because remember 1 plus cotangent squared is just cosecant squared. So this denominator becomes cosecant squared. And then if I just flip that, it ends up to be sine squared. That's simplified. Now on the other side, if I did work with that ugly expression, I could multiply top and bottom by sine squared to clear the fraction. So let me show you what I mean. Multiply top and bottom by sine squared x sine squared x. And this is like over 1 over 1. So you're just multiplying in the numerators. So in the top, 1 times sine squared is simply going to be sine squared, and this becomes sine squared x over. In the denominator, the sine squared over 1 times 1 is just going to be sine squared, plus, and the cosine squared over sine squared, the sine squareds cancel, and you just have cosine squared. And then going back to our identity, sine squared plus cosine squared is 1, which just gives you sine squared. So although the directions said to write it in terms of sine and cosine, I kind of ignored that, even though I probably shouldn't, because it is nice practice to work with complex fractions and trig functions. And I just used the identity. It was much easier for me. In number 6, it says perform the operation and then simplify the results. So the operation here is subtraction of fractions. And whenever we work with fractions, we need a common denominator. So remember the cosine minus x, this is one piece. And the cosine of x plus 1, that's one piece. So if I wanted to find a common denominator, that would actually be cosine x minus 1 times cosine x plus 1. So the LCD, going back to fractions, is going to be cosine x minus 1 cosine x plus 1. Now I'm going to multiply the first fraction by the plus 1, top and bottom. So cosine of x plus 1 over cosine of x plus 1. And then the second one would be cosine x minus 1 cosine of x minus 1. Oops, sorry, an alarm going off. First fraction, cosine of x plus 1 times 1 is simply cosine of x plus 1. And then we have our denominator, cosine x plus 1 cosine of x minus 1 minus 1 times the cosine of x minus 1 is just cosine of x minus 1. And then our denominator, cosine x plus 1 and cosine x minus 1. Okay, so let's just look at this for a second. Denominators is the same. I can combine in the numerators. Don't forget that you need to distribute that negative on the second fraction. So it'll be a minus cosine of x plus 1. Our numerator is going to be cosine of x plus 1 minus cosine of x plus 1. All of that over this denominator. And you could multiply it out if you wish. Something you should notice from algebra is that in the denominator we have two terms and two terms. They're exactly the same, but one's a plus and one's a minus. So I don't know if you recall conjugates. Conjugates had that property that when you multiply them, it's going to be the square of the first minus the square of the last. Those middle terms are going to cancel. In the numerator, this cosine x cosine. So cosine x minus cosine x is just 0. So I get 1 plus 1 or 2. And in the denominator, this becomes the square of the first. So cosine squared minus square of 1 is just 1. If you wanted to multiply that out, you would have cosine squared x minus cosine of x plus cosine of x minus 1. So you could see that these middle terms cancel because they're conjugates, and you get the square of the first minus square of the last. But now cosine squared minus 1, it's not quite our identity. Recall that our identity is sine squared plus cosine squared is equal to 1. So if I were to minus 1 from both sides of this equation and minus the sine squared, I would get cosine squared x minus 1 is equal to negative sine squared x. So I can replace, because this is not really simplified, the cosine squared x minus 1 with negative sine squared. So it's going to be 2 over negative sine squared x. And then I can write that in a better form or a nicer form. So remember, sine reciprocal is cosecant. So this can be written as negative 2 cosecant squared x. And that is completely simplified. So we performed the operation, we added these ugly fractions, but remember, they're just fractions, so treat them the same as you would any fraction. And then we kind of used our identities to simplify this. The next thing we're going to do is we're actually going to go through verifying identities. So when we verify identities, you're given the equation. You just have to verify that that equation is true. And this is what we actually call a proof in mathematics. So whenever you're asked to verify something, you're actually writing a proof. Now, it's solved. You don't have anything to solve. So the key whenever you're verifying is to show all the steps, because you're supposed to verify that one side is equal to the other. So you have to show all the steps. Sometimes it gets confusing. So what you really want to do is you want to understand your identities and become familiar with them, because you're going to use them a lot and in different ways. As in our previous example, when I rewrote the sine squared plus cosine squared equal to 1, so I could get cosine squared minus 1. So you're going to need to be familiar with your identities and how you can change them up. So for example, sine squared plus cosine squared equal to 1. That's cosine squared equal to 1 minus sine squared. That's another way to write that Pythagorean identity. Another thing you do when you verify is it's always easiest to start with the complicated side first and then simplify it so it looks like the other side, if there is a more complicated side. If you get stuck, just try writing everything as sine and cosine, because that's more familiar to us. There's going to be some algebra techniques that may come up, such as combining fractions or factoring. And in our prior example, we combined with fractions. So here's a couple examples. If you're adding the fractions here, which would be this cosine over sine plus sine over cosine, you could write them with their common denominators. So the first fraction, I multiply top and bottom by cosine. The second one, top and bottom by sine. And then once they have their common denominator, you just combine the numerators. So it becomes cosine squared plus sine squared. And then using the identity, cosine squared plus sine squared is 1. So we get 1 over sine cosine. So that is a trick we use a lot, is cosine squared plus sine squared is equal to 1. Another example, if you had cosine squared plus 2 cosine plus 1, that's actually the form of a quadratic, and it does factor, but it's really hard for some people to see that this would factor as cosine of x plus 1, cosine of x plus 1. So going back to our algebra, what's irritating is this cosine. That's what's bothering me. So if you did a simple substitution, you can't use x because x is already being used, so maybe y. Let y equal cosine of x. And then we can rewrite this as cosine squared of x becomes y squared, plus 2 cosine becomes 2y, plus 1. And that might be easier to see that it would be y plus 1, y plus 1. So once it's factored, then you can replace the y with cosine of x to get cosine of x plus 1, cosine of x plus 1, or in other words, cosine of x plus 1 squared. Look for conjugates. That sometimes comes up whenever we're working with fractions. In this first example, we have cosine squared over sine of x minus 1. So if it was sine squared minus 1, then I could use the Pythagorean identity, but it's not. So all I have to do is simply multiply it by sine x plus 1, but what I do to the bottom, I have to do to the top. And that will give me those conjugates that we talked about. And when you have conjugates, it ends up being the square of the first minus the square of the second term. And once I have sine squared minus 1, I can replace that with the negative cosine squared. Notice in the top I decided not to distribute the cosine squared because I thought, ooh, something might cancel. And it does. So remember, whenever you have a fraction, you can cancel common factors in the numerator and denominator, but you have to make sure everything's factored or multiplied. So now this is cosine squared times whatever's in the parentheses. I can reduce by cosine squared in the numerator and denominator to get negative sine x plus 1, which in turn, if I distribute that negative, becomes negative sine x minus 1. Again, these cancel, but I still have this negative here that I have to distribute. So we're going to practice this. And then 10.2, we're going to work some more with more identities. So it says verify that the equation is an identity. Again, we're not solving, it's solved. There's the solution right there. It says tangent divided by secant is equal to sine. We just have to verify this is true. So the more complicated side to me is tangent over secant. That's where I'm going to start. Now, whenever you verify, you always have to write down the side that you're starting with. You cannot skip this step because you have to let your audience know where you're starting. So tangent over secant. What I'm going to do is I'm going to separate these into tangent times 1 over secant, because it's easier for me to see and switch everything to sines and cosines. Now, the reason why I'm going to switch everything to sine and cosine is because I see that on the right-hand side, I have to end up with a sine in there. So I might as well switch everything to sine cosine. And tangent's going to be sine of theta over cosine of theta. And then 1 over secant, reciprocal is cosine. And at this point, I could see that these cosines will cancel, and I will end up with sine. And that's it. I've verified. I started from one side and I worked my way to the other side. Okay, no skipping steps here. Let's try another one. This one's a little bit more complicated. And both sides to me are kind of ugly. So I'll do it two ways. I think I would rather start with the subtraction on the right-hand side because I know I have to somehow combine those so that I get one expression or one fraction. So it seems easier to me, now it may not be to you, for me to start with secant of theta minus cosine of theta and write that as secant would be 1 over cosine. And then I have cosine over 1. And the reason why I did that is because I'm trying to create a fraction because the left-hand side is a fraction. So now I have a subtraction of fractions. I could see that I need to multiply the second fraction by cosine over cosine. So that I have common denominator with my fractions. This becomes cosine squared theta over cosine. And now that I have common denominator, I have 1 minus cosine squared in the numerator over cosines of theta. So remember, this has to end up looking like sine squared over cosine. I've got the cosine in the denominator. I don't have the sine squared in the numerator. However, we have the Pythagorean identity. Did sine squared plus cosine squared. Let me write this off to the side. Sine squared theta plus cosine squared theta is equal to 1. So if I simply minus cosine squared from both sides, I have sine squared theta is equal to 1 minus cosine squared theta. So I can replace the 1 minus cosine squared with sine squared. And that's it, I'm done. I worked from one side to the other. Now notice that if you don't write down the first step where you start from, you're not actually verifying that secant minus cosine is equal to sine squared over cosine. If I didn't write down the secant minus cosine, all I've proven is that 1 over cosine minus cosine is equal to sine squared over cosine. So again, it may seem tedious, but you do have to write down your first side that you're starting with. You have to go all the way to the other side, and you have to show all the steps because you're verifying. You're not solving, it's already solved. And that's it for this section.